Alright, so in this video I'm going to be explaining another important article with the title Probabilistic Graph Rewiring via Virtual Nodes. The reason that people use virtual nodes because unlike transformers and graph transformers, the graph neural network has a very local structure, and when you want to do message passing between two distant nodes, you have problem. That's why people do some kind of graph rewiring. Of course, they should make sure that they don't change the topology of the graph, otherwise it's very dangerous, and it reduces explainability. So this paper in 2024 is dealing with probabilistic graph rewiring. Message passing graph neural networks have emerged as a powerful paradigm for graph-based machine learning. Despite their effectiveness, message passing neural networks face challenges such as underreaching and over-squashing, where limited receptive fields and structural bottlenecks hinder information flow in the graph. While graph transformers hold promise in addressing these issues, their scalability is limited to quadratic complexity regarding the number of nodes, rendering them impractical for larger graphs. Here we propose implicitly rewired message passing networks, a novel approach that integrates implicit probabilistic graph rewiring into message passing neural networks. By introducing a small number of virtual nodes, for example, adding additional nodes to a given graph and connecting them to existing nodes in a differentiable end-to-end manner, it enables long-distance message propagation, circumventing quadratic complexity. So you see that overview of how it implicitly rewires a graph through adding the virtual nodes, and it uses an upstream message passing neural network to learn priors for connecting original nodes with virtual nodes via edges, parameterizing a probability mass function. A probability mass function conditioned on exactly k constraints here. Subsequently, we sample exactly k edges from the distribution for each original node, connecting it to k virtual nodes. We input the resulting graph to a downstream model, typically message passing neural network for final prediction tasks. So you have a graph, then in the upstream message passing neural networks, we are creating these by exactly k sampling, we are creating k edges because they are connected to k virtual nodes. So this is a virtual graph. This type of connection that with his ... it means it is a virtual graph. And on the backward path, the gradients of the loss are approximated through the derivative of exactly k marginals. So this is message passing. We aggregate messages and then we update them. Then we need a readout because we need to represent a graph for example, graph classification. So they introduced this model, but first they need to sample edges. Sampling in general is has a discrete nature. That's why sometimes you need Gumbel softmax to approximate the argmax and those tricks. So consider G as an attributed graph of order n. The upstream model transforms an adjacency matrix along with its node attributes into a set of unnormalized node priors, with M denoting the predefined number of virtual nodes. The matrix of priors serves as the parameter matrix for the conditional probability mass function. So we have this assignment, it's an n by m matrix. It's an assignment matrix. Why? Because we have m virtual nodes, but we have n nodes. We have n nodes, we have m virtual nodes. So we need to assign that these nodes belong to which virtual node. This assignment has, of course, H has a discrete nature. I mean, it's a hard nature. It's not a soft, it's hard. So it's either 0 or 1. Each entry of this matrix is either 0 or 1. And so let's see how they are learning it. So each row of the sample assignment matrix has exactly k non-zero entries. So each row of the matrix represents probability of assigning node I to reach the virtual node. Here we outline the message passing scheme after adding virtual nodes. So initializing virtual node embedding. Before executing interhierarchical message passing, we need to initialize the embeddings of virtual nodes. To that, given the node assignments, for V, we can effectively divide the original graph into several subgraphs, where nodes sharing the same assignment label are grouped together to form an induced subgraph. Formally, for any virtual node, we have the induced subgraph. So, the initial attributes of the virtual node C, this virtual node C, because we have an edge set now, so the initial attributes of node C, virtual node C, are defined by node features of its corresponding subgraph. So this is G of C is a subgraph that is generated by this C virtual node. All of them we call it G sub C. So we need the message passing only on this to represent the node features of that virtual node. Alternatively, we can generate random features for each virtual node as initial node features or assign unique identifiers to them. So then we update the virtual nodes. In each step, we collect the embeddings from original nodes to virtual nodes according to our assignment and obtain intermediate virtual node embeddings. So we assume the virtual nodes form a complete undirected unweighted graph, and we perform message passing among the virtual nodes to update their embeddings. That is, at step T, we set this. Note that the virtual nodes is a complete graph, and it is undirected. So we can perform message passing the virtual nodes to update their embeddings. This is update, this is aggregation, so it's very common. And then finally we redistribute embeddings from virtual node back to the base nodes. So because we are distributing, I'm saying we are redistributing. This distribution, this is distributing function. This is because traditionally you know what is aggregation and update, but they added something more interesting, distributing function that incorporates embeddings from virtual nodes back to original nodes. This is the novelty of this paper. They update not just with node itself and aggregated messages, but also with the distributing function. And so this is how they connect the embeddings of the virtual nodes that we have calculated before. Now the gradient estimation In the context of our downstream message passing neural network, we define the set of learnable parameters V and group these with the upstream model parameter into a combined tuple. So, for long distance nodes, for over squashing, these two datasets are amazing and very important. And I've seen it in several papers that they use these two datasets. Of course, some people use these datasets as well. But so they compare different models, even GCN. If you compare GCN with this model, let's look at the improvement. So green is the best model. Blue is the second model. And finally, they compare to approaches that are reported in this paper. For example, let's compare graph isomorphism network with this approach. You see that, for example, for this graph classification dataset, we see that from 82, we have 4% improvement. For protein, we have some improvement. For MuTag is a huge improvement. Of course, MuTag is a very easy dataset.